we're lucky to have Jimmy, who's a third-year maths student here at work, and you're going to be telling us about Lassa fever. So
yes,
take it away.
Yes, I am. I'm Jimmy. I'm a third-year PhD student. That's what I have written down. I have to read it. I've been basically doing all my PhD on modelling this disease called Lassa fever in Nigeria. Basically, I've been just trying to fit as many models as possible to the same data set and hopefully seeing if I can get a PhD at the end of it. So Lassa fever is a hemorrhagic viral disease primarily spread by rats, which can cause you difficulty breathing, bleeding from the eyes, nose and gums, vomiting, diarrhea, and seizures. A lovely infection that's endemic to West African countries such as Ghana, Guinea, Sierra Leone, and notably Nigeria. Has an estimated about 100 to 300,000 infections a year, with about 5,000 deaths occurring annually. It is relatively neglected, in fact so neglected that it's not even called a neglected tropical disease, but in the past year it has had at least started a vaccine trial for it, which I think is positive. Lassa fever, particularly in Nigeria, has had since 2017 an epidemic that's happened. Well, it's unexplained as of now, but it's been routinely happening for the past was it now 6 years, between the months of January and March. Not only that, but the hundreds and sometimes thousands of confirmed cases that they get in Nigeria mostly happen in 4 of their 36 states, and those are normally towards the south anyway. You can see in that picture on the left there where there are slightly bigger red splodges, the Edo, Ondo, Bauchi and Ebonyi. Right, transmission typically happens when people come into contact with the rat Mastomys natalensis, either by eating them, or sometimes the rats will enter your home and they can contaminate your food, normally by urinating or defecating on it. Lovely. While you can pass it on to someone else, Lassa fever, unlike COVID, isn't transmitted by water droplets in infected individuals' breath. It's done primarily by transferal of bodily fluids, which occurs most often in nosocomial settings without proper PPE. For these reasons, the human-to-human transmission rates are infrequent, and outside of under-equipped and prepared medical environments don't account for what we see in the data, what the spatial and temporal dynamics that we see of this disease. It's specifically the rat-to-human interaction that drives these epidemics. I want to know how and why it happens in such a way that such few places have so much of the see a sharp rise in cases in a specific time frame. If we can learn these epidemiological mechanisms behind this disease, then we can prevent bigger epidemics and spread to the international community with any luck. So this is the model. I know not everyone's an epidemiologist here, so I will try to keep this brief because it's rather messy and ugly, isn't it? To investigate this, I've made compartmental models that simulate the population dynamics within an epidemic. This divides the population into compartments where each box contains only the people in the same stage of infection. I'm sure many of you have come across this, well, maybe not, but the MSc students will soon. I think it's this term you have something for that. The model that I've been using to start my investigations is as follows. It's a sort of two-system thing with subscripts for rats and humans, separating them too. So for the humans, we start off as being susceptible to the disease until you come into contact with either a person or a rat that's infected, at which case you become exposed to the disease, where it incubates within you for about 14 days. And that range is the range that they give on World Health Organization is 2 to 21 days, which is a pretty big and useless range. After which you become infectious and you can infect other people. Infectious people are subdivided, if you can make out that little flow chart in the bottom left, into two different ones. This is being you're either asymptomatic, which happens at about 80% of the cases, and the rest you have rather not so mild symptoms like I described before, and a higher chance of dying. And then eventually you'll recover, normally about 2 weeks as well, if you haven't died. The rats have their own dynamics as well, and for this I've chosen susceptible, infected, and recovered. Some of you may notice a weird little function F for the rats. We'll come back to that later, and for now it's just the identity function, NR. So, moreover, to simulate the natural and seasonal reproduction rates that we observe in Mastomys natalensis, I have borrowed this ecological function called the periodic Gaussian function. It's a 3-parameter cyclic function. Again, it's not very interesting, I think, but I'm just going to explain it quickly. It's been used to help model population dynamics of other mammals, such as other than rats, like bats and I think wolves or something, seals actually. This works far better than other more standard functions that you might have seen, like perhaps putting in a sinusoidal function or a logistic equation into it. Furthermore, I can normalize it. That little k out the front can be normalized so that the population remains constant year on year, which we kind of expect with a rat that's been endemic for the area for a while. Right, and then I go on to fitting. I don't know how many people have heard of approximate Bayesian computation, but that's what I've been using. It's a rather nice sort of black box thing that I can use to fit models. And for this, I particularly have data from the NCDC, the Nigerian CDC case data for this, which is very kind of them to supply. They haven't spoken to me very often since, so I would like some more from them, but oh well. For those unfamiliar with ABC, we start off with prior beliefs on what our parameters we don't know about. So transmission rates, you can't possibly measure that really. We're going to start off with some probability distribution and assume that's what it looks like anyway. We will then draw samples from these priors, put them into our model, simulate our data, see how close our simulated data is to our observed data, and if it's close enough, we accept that parameter set. We end this algorithm when we have enough particles that we're happy with. There are several varieties of this. I've got my own little one that's not up here. I'll briefly explain that after this. ABC rejection is just what I explained. SMC is a little more fruity. You get a sequence of tolerances that decrease. So the first generation, you do the same thing as the ABC rejection, but for subsequent generations, you will then evolve those accepted parameters through parameter space, getting closer and closer and closer to your observed data, hopefully. And hopefully the parameters, the posterior distributions look nice at the end, which is really what I want out of it, just that it looks nice and sensible, which doesn't happen very often. My own modified one is I've done myself. I haven't seen this in a paper or somewhere. I don't know whether it's grounded in anything statistical, but to the probable benefit of no one, you're going to hear about it now. So instead of giving the algorithm a sequence of tolerances, because I found that to be very hit and miss, I will give it a multiple k and a quantile q. If I want a total of n particles, say 2,000 particles at the end of this, I will draw k times n particles and then just choose the best n at the end of this. That's a very nice and quick way to get the first generation done. I will take stock of this this first generation and subsequent generations, order them in with respect to the distance from their simulated data and the observed data. And then with my quantile, so I'm trying to make the next generation basically the best qth quantile of the previous generation. So if I set q to be 0.5, then I'm setting my error, my acceptable tolerance for the next generation to be the distance that I got for my best 50th or 50th percentile of the ones that I got previously. So that would be the distance of particle q times n. Yep, so that's just there. You then pick a smaller ring around your data, and then you carry on as you were before. You evolve your particles through space, and hopefully you get closer and closer, but not always. So these are the results of the best fits. This is to the national scale of data, and as you can see, it kind of fits the general trend. The black points on the left, the simulated data on the left is the actual data. Excuse me. The orange is a cross-section of all the accepted particles in my final generation. I think this was about 12 generations to then get to the end. And this cyan, which I think you can see from here, is the best fit. And this replicates the year-on-year trend and comes up with some interesting posterior distributions, which are on the right. These are marginal posterior distributions. Technically, it's a 5-dimensional object, but I can't really plot a 5-dimensional object and you guys to really understand it. Top left, we'll go through the parameters very quickly. S is a parameter that controls the width of the birth function. So if you cast your mind back to that little hilly little function I showed earlier, the bigger the S, the tighter it gets. In fact, as it goes to infinity, it becomes a Dirac delta function. So this very high S makes it very concentrated, the birth rates for the rats. The beta RR, the rat-to-rat transmission rate, is quite high. In fact, R0 has a value of over 200 in this, in most of these ones, which we'll come back and talk to you about later. Human-to-human transmission rate is comparatively tiny. In fact, in this model, human-to-human infections only account for about 0.5% of the total. So very almost exaggerated and quite heavily leaning on the spillover events to rats. Beta RH is rats to humans, sort of dependent on the number of humans there are and the number of rats there are. I've done some sensitivity analysis on that. That's also coming up, lucky you. And the last one, bottom left, phi is the, again, for the birth rate function, that is the date of the minimum reproduction rate for the rats. So this is in late May, early June, and therefore this corresponds to a late November, early December maximum. And this results in the rat population exploding in that time. I've clicked on something that I shouldn't have. There we go. Yeah, there we go. So here we see the rat dynamics underneath what we can actually detect. It's the exceedingly high R0 for the rats makes this sort of rat epidemic near instantaneous. It goes, the rats, when it becomes the breeding season for the rats, the susceptible rats don't really appear at all. They immediately become infected, and then you see a big green hill where the infected rats are, and that's what happens in this model, that those are then driving the infections in humans. On the right, you can see the effective reproduction, where the threshold for infective, the effective reproduction rate for rats, and that is the expected number of rats that a single rat will cause to be infected at time t. R0 is when t is 0, so when there's only one infected rat, then every other rat is susceptible. And this will go over 1, so that's that magical threshold where the number of infected rats will start growing, and that happens between early December and sort of mid to late December, which acts as a sort of indicator for the risk that then comes on to humans. So as I said, I did a little 6-parameter variant. I did mostly on the number of infected rats at time 0. In the previous model, I had set that to be at endemic equilibrium. Again, we sort of assumed that the rats have had this for ages, and it's only now that we're able to detect the problem. That's why we have this, but that's been underlying for a while. I've changed it to 0.5, as in of the population, so 50% of the population to 1/1000th of the population, and it kind of changes it as you'd expect. If half the population of rats are infected at the beginning, then the number of infected humans that we expect tends to be a lot higher than we observe, which, yeah, that's fine. But if you fit it as an individual parameter, then it sits at around 10% of the population. So, you know, when I said that mystery function f that we were looking at the model, and we'd come back to it, well, we're here now. The contact density function is a look at how transmission and contact behaviors, particularly of the rats, change with the density of the population. Humans, like us, like to maintain a certain distance from each other. So London has about 8 million people in it. Coventry, I think, is a couple of 100,000. You're not going to, if you go into the centre of Coventry, centre of London, you're not going to come into contact with 50 times as many people. We like sort of staying at a certain distance away from each other. So we can consider the population as if it were in its own box, literally, as I've compartmentalized it. In human-like behavior, we are density independent. So the more people we put into that box, the box grows with it. And that's that horizontal line you see there. That's that first function. That's what I've been working with. The second one is population dependent, linearly dependent. So if you put twice as many people, twice as many rats into the box, then you come into contact with twice as many people. And that's that yellow line that goes straight up diagonally with it. And then the other two functions, power law and a sigmoid function, those are in between that. Those are just sort of variety of functions that I want to see. Is it possible to model it any better than I already have? And here's another modeling selection algorithm for you, ABC. Again, I'll be very quick. The only added thing onto this is that at the beginning, we have a prior for which model it is. We select the model, and then we have segregated inputs and priors for each model, because sometimes the model has more parameters than the other ones. And that's how that works at a glance. So very quickly, out of the 4 models, again, the results look very, in fact, near identical, I dare say. But it can be done that it wants to go either frequency dependent or sigmoid dependent. And I think that is because the rat-to-rat transmission is so high that it really doesn't matter about anything else. It immediately wants to skyrocket the number of rats that are infected to then drive the human spillover events. And those are the parameters, posterior distributions. Again, very similar, minimum reproduction rate, reproduction rate in around early middle of June, high rat-to-rat infection rates, low human-to-human rates, and again, about 10% of the rats are initially infected. So, metapopulation, I missed out an introductory slide to this, never mind. I mentioned earlier that the case data in this is very spatially localized. Why would I mention that if I'm not going to do anything with it? Well, I did. And that's what I've been doing recently. So the concept behind a metapopulation is to split your population up into geographically localized spaces. So in this case, there were the 4 states that I mentioned, and then the remaining one. So I want to split each of those compartments up into 5, and then model them at the same time with the parameters, with the data separated, and have it all go on at the same time to see what differences there are. And that's what I want it to look like. But psych, no, it didn't work like that. This is the fits when I just do them at a state level individually and then ignore the rest. That's what happens when I make the model do it for 3 states and try and do it all at the same time. And the problem is that there's about 5-6 parameters per each metapopulation. You do it for 3 to 5, then suddenly you've got 30 odd parameters, and then also there's some migration parameters, the number of people that go to each of the other states. They can move over states. They're not isolated in each of those states, and that balloons the number of parameters up to about 40, and it doesn't like it really. So big sad. So at the end of this, the model shows that I can kind of replicate the trends in case data. I want to do this further with the metapopulation to see can I work out what the differences are between all the other states and the states that have most of the case data. That's about that for the discussion of this, I think, in my head. Future work, I need to finish that metapopulation model. I'd like to investigate covariates such as rainfall in this. There's been a handful of papers that have linked the number of rats to rainfall, the number of infective or prevalence of Lassa fever in rats with rainfall, and then also the number of cases that happen in humans with rainfall. So what I want to do is to marry it all up where rat population and dynamics are influenced by the weather and environment, which then influence, and what is this little dance of Lassa fever that we're doing here? Can we influence it positively for us somehow? Can we prevent more infections? Can we predict stuff? Can we implement implement control measures? Can we then start predicting when epidemics will start happening? So NCDC are kind of worried about climate change. Will less rain or earlier rainy seasons change when the epidemics start happening and the size of them? So there we go. That's the end of it. Well done.